One thing you might find interesting or surprising, knowing that we can take the derivative of any function. If we ask you what the derivative of tan of cos of x cubed plus 1 is, we can work through that. And it'll be sec squared of the inside. And then we do the chain rule, so we take the derivative of the cos, so times the derivative of cos, which is minus sine of what was inside that, should be cubed, x cubed plus 1, times the derivative of the inside of that, which is 3x squared. And with the combination of those rules and the rules for products and quotients, there is literally nothing you cannot differentiate. Okay, maybe easy is not the right word, but it's always doable. So derivatives are always doable. Pardon me. So it might be a little bit surprising, but it turns out that finding antiderivatives going back from this function to this one is not always easy and not, in fact, always possible in terms of finding a formula. So we're going to spend a lot of time, a lot more time than we spent on derivatives, with strategies for going from a function on this side to a function that's the antiderivative. So we're going to explore some techniques for that now. One example might be this function here. What kind of antiderivative might we hypothesize? Well, one of the things we could say is maybe that's this is like a 1 over something. So ln of x cubed plus 1 plus a constant. So maybe that's what the antiderivative is. Well, if we take a look at that, remember we can always check. There's a gold standard for anyone's proposed antiderivative. We check by differentiating. And if we check by differentiating, we're going to get the derivative of ln of x cubed plus 1. And the derivative of that is 1 over x cubed plus 1. And fantastic, that's what we had to start with. Oh wait, but there's a product rule we need to use. We're going to get 3x squared after that. Well, that's not in the original. In the function that we were asked to integrate, it was just 1 over x cubed plus 1, and so we're out of luck with that. So that means this is not the antiderivative. Well, I can maybe hypothesize some other formulas. It's almost like an arctan if you wanted, or the derivative of arctan, yeah. That's 1 over x squared plus 1, so maybe it'd be something like x to the 1/3 or something, plus, no, we don't need plus 1 even, to the 2/3, let's do the, sorry, 3/2, let's do 3/2. So we're guessing, we're trying to take a stab at these things, and again we can check. If we differentiate this, if we differentiate arctan of x to the 3/2 plus constant, we're going to get 1 over what we have inside, x to the 3/2 squared plus 1. And yay, this is actually 1 over x cubed plus 1. That's good. But the chain rule comes back to bite us again, and we have to take the derivative of the inside, and that's bad. Again, not in the original, and so this is no antiderivative either, no better than the ln. And the short answer to all of this is whatever you try, I guarantee if you find a nice closed formula for it, it will not be the antiderivative. Whenever you go back and check, it's not going to work out. So the problem with this function here, it actually has no closed form antiderivative. That's just the way it is. In fact, this is an impossible case in the sense of finding a simple formula, or even a complicated formula without sums, of the antiderivative for 1 over x cubed plus 1. That's just the way it is. So that's our first problem. Some things will not be anti-differentiable, even though everything was differentiable before. So having confronted the problem of integrals that have no solution, we're going to try to find the middle ground where there are solutions, though they might be more complicated than anticipated. For example, if we're trying to find the integral or antiderivative of cos of 5x. Notice it's an indefinite, we're just trying to find the antiderivative function. We might guess something like sine of 5x plus a constant. So this is what we're going to call the guess and check method. Hey, what's the derivative of sine? Derivative of sine is cos. Well, if I need a 5x inside, I better have a 5x inside here. And what we can do is then check. Is this exactly right, close to right? We're going to take the derivative. And when we take the derivative, we're going to get a cos of 5x, perfect, plus 0, that's fine. But we also have to take the derivative of the inside, so we're going to get a times 5. Again, what we're going to try to do then is compare these two. And if they're not the same, then we do not have the right answer for our antiderivative, or our indefinite integral. We have 5 cos of 5x's here. We have 1 cos of 5x up here. They're not the same yet, but we can fix that. Off by a constant is super easy to fix. We just divide everything by 5. And when we cancel the 5's here, we're going to get cos of 5x. And we go, that is right. That's exactly what we want. And so the antiderivative of cos of 5x is 1/5 sine of 5x plus a constant. Nice. And we checked it, we verified it with a quick calculation like this. Now what if we try the same thing again with, instead of 5x, let's make it x squared. Well, we could guess, again, that the solution is going to look something like sine of x squared plus a constant. And let's check that that actually works. We're going to take the derivative of sine of x squared plus a constant. And when we differentiate that, we're going to get cos of x squared. That's good, that matches. And then we're also going to get a 2x multiplier from the derivative of the inside. Now, we fixed that last time, so that's bad. We don't want that 2x. So what did we do last time to fix that? Well, we sort of divided by that. We said, well, let's divide by that extra factor. And here's where that factor being not just a fifth, but something involving x, gets us into trouble. Because now we need the quotient rule. Once we make that change, we're actually going to find the derivative of sine of x squared over 2x, and I almost guarantee you there's no way that, with the quotient rule, is going to turn into a nice cos of x squared. And so that fix doesn't work. And so by changing this from a linear to a quadratic inside, we get all sorts of horrible chain rule effects that can't be easily fixed by tweaking our function. So that's a real problem here. And in fact, the integral of cos x squared is another one of these functions that has no closed form, in other words, simple formula, closed form antiderivative. It does not exist. There's no simple way to write that antiderivative out. We can find the area underneath the graph with some numerical methods, but this, we're stuck with it. There's no closed form formula we can find. But what if we take a quick peek at a variation? What if we had cos x squared, but with an x out front? At first glance, this might seem like it's making it more complicated, but trust me, let's see how this works. If we went back to our original guess from last time, hey, I wonder if, because of this cosine part, we should have a sine here, sine of x squared. The derivative of sine is cos, we'll need an x squared inside. When we check that, and we take the derivative of sine of x squared, I'll get that right yet, plus a constant, we're going to get cos of x squared times the derivative of the inside at 2x, and the derivative of plus c is 0, and then we compare these two. Are those identical or not? Well, they're actually pretty close. In fact, the only thing they're off by is a factor of 2. I have a factor of 2 here that is not in the original, and as we saw in an earlier example, fixing that is not a problem at all. And if we work that all the way through, we get the halves canceling with the 2, and we get exactly x cos of x squared. So in fact, what we've shown is that if we differentiate 1/2 sine of x squared plus a constant, we get x cos of x squared, which means if we integrate x cos of x squared with respect to x, we're going to get the 1/2 sine of x squared plus c. So nice. So in fact, this integral, which looked more complicated, is actually easier than the simpler one without the x. Here we have an x cos x squared, here there's no x, but the guess and check worked because we have the term that will come from the chain rule. We know we're going to need a cos of x squared's antiderivative, which will be a sine of x squared, which means we'd better have the derivative of the inside lying around somewhere. If we're going to move back more easily to go from this to here, we get a simpler answer when we antidifferentiate. And this term here, this integral here, has no x term outside. And that actually causes us problems because we're missing something that would naturally be generated when we differentiate later on, or to check. So it's a bit of a new world when we look at integrals compared to derivatives.